So the whole reason we did caches with performance, so let's talk a little about the performance impact of caches. So what is a cache miss ratio? So miss ratio is one way to talk about the effectiveness of caches, and the cache miss ratio is the percent of cache misses. So this is the number of cache hits over the total number of memory accesses. So let's take a look at some miss ratios. So here are miss ratios for 4 applications for different size caches. Here's one application, LBM. So for this LBM application, we can see it has a miss ratio of 10.5% up to a 64 kilobyte cache. When the cache size increases to 256 kilobytes, its miss ratio falls to 6.5%. And then finally, when it gets 8 megabytes of cache, its miss ratio is going to fall all the way down to 3.5%. Here's another application, bzip2. It has very different behavior. At a 32 kilobyte cache, bzip2 has a 3% miss ratio, and its miss ratio falls linearly all the way down to about a 0% miss ratio at 4 megabytes of cache. So question, what happens to performance when the miss ratio goes down from 10.5% to 3.5%? Well, it's going to be faster. The application is going to run faster because it's missing less in the cache, and missing in the cache is really slow because you have to go access the main memory. However, you don't know how much faster, just that it will probably be faster. So to figure out how much faster, let's take a look at the average memory access time. So this is the average numbers of cycles for a memory access. And how do we compute this? Well, it's the amount of time it takes for a cache hit plus the percentage of cache misses times the amount of time it takes for a cache miss plus the penalty for missing. So the miss penalty is the time we spend after looking in the cache. So when we miss on the cache, we're going to first look in the cache, and that will take some time, and then we're going to spend some more time going to DRAM to get the data. So let's take a look at an example here. So here we have a hit time of 1, a miss time of 1, and a miss penalty of 3. So if we have a memory access and it's a hit, that's fine. Another memory access, if this one's a miss, we pay that miss time. That's the time it took to go look in the cache, and then we pay a penalty. So this is the total amount we pay when we miss in the cache. So if we have another memory access, it's a hit, and then another miss, pay another penalty, and another hit. Now, what is the average memory access time? Well, the percent of misses here are 2 out of 6 memory accesses, so 33% of the time we're missing. So our average memory access time is 1 cycle for each hit, plus 33% of the time we spend 4 cycles, 1 cycle for the miss and 3 cycles for the penalty. So on average, we're spending 2.3 cycles for every memory access. So let's take a look and see how that affects applications. So here we're using our data on miss ratios, and we've got some information about the machine. The machine has 100 cycles to DRAM and 1 cycle cache access time for hit or miss. So what is the average memory access time for LBM? And we're going to look at a 256 kilobyte cache. So a 256 kilobyte cache, we have about a 6% miss ratio. That means the average memory access time is going to be 7 cycles per memory access. How about if we had an 8 megabyte cache? So an 8 megabyte cache, our miss ratio goes down to 3%. So here we're going to have an average memory access time of only 4 cycles per memory access, or just about half as much. Let's take a look at another machine. So here's a machine with 100 cycles to DRAM, but this time 2 cycles to access the cache. Let's take a look at bzip. So for bzip at 256 kilobytes of cache, it has a miss ratio of 1.5%. So its average memory access time is 3.5 cycles per memory access. So why is bzip's average memory access time with a much smaller cache almost the same as LBM's with a much larger cache? Well, the answer here is that the cache is much slower. So the cache on machine 2 takes 2 cycles and only 1 on machine 1, and this really hurts our AMT. The application difference is the difference in the miss ratio. So what we saw in the application difference is that LBM had a 6% miss ratio and bzip had a 1.5% miss ratio. But the reason that bzip is so much slower, even though it has this the reason why bzip is just about as slow, even though it has a much lower miss ratio, is because the cache on machine 2 is much slower. So how much does cache behavior affect performance? So cycles per instruction. Now we've got a machine where we have a 100 cycle miss penalty, say we have a 3% miss ratio, and we have 1.33 memory accesses per instruction. So that's one memory access for the instruction, and then 33% of the time we access data. So there's a CPI of 1 for normal execution. So what's the performance? Well, the performance, the cycles per instruction in the machine, is going to be the cycles per instruction needed for execution plus the memory stall cycles per instruction. So what's this going to work out to? Well, we have 1 cycle per instruction normally plus 1.33 memory accesses per instruction, and the average time for those memory accesses is 3% of the time we spend 100 cycles in our miss penalty. So that means we're going to have 5 cycles per instruction because of this because of the slowdown due to the memory. So with this cache behavior, the processor is 5 times slower than ideal. So this tells you that caches are really important. In fact, this is somewhat of an understatement. Caches are the most important thing for performance today. If you want to make your code run fast, the most important thing to do is make it work well with the cache. So how much does the cache matter? Let's take a look at some applications. So here's an application, and what we're going to do is change how much cache it gets. So as we reduce the amount of cache it gets from 8 megabytes to 1 megabyte, you can see it doesn't slow down at all. What it does do is it accesses more memory, more data from the DRAM. So this is an application that's insensitive to cache size. When it gets less cache, it just goes and gets more memory from the DRAM but doesn't slow down. Here's an application. As it gets less cache, it slows down a lot. And at the same time, it goes and gets more memory, more data from the DRAM. So this is an application that's sensitive to how much cache it gets. You need to make sure you get a lot of cache to get good performance with this application. Here's a third application. You can see this application doesn't change its performance at all depending on the cache size. But when it gets less cache, it uses a lot more bandwidth, gets a lot more data from memory. So this is an application that's insensitive. So if we look at this, we can see that when an application gets less cache, it needs to make more accesses to memory. And that makes sense because it's not finding the data it needs in the cache. We also see that some applications are more or less sensitive than others. So understanding the performance impacts of caches is really tricky. And in fact, the data you're seeing here is from some of the research we've done here at Uppsala to try and understand these performance sensitivities. So one thing we've mentioned earlier in this lecture is that we need to have separate instruction and data caches because we need to access the instruction and data memories at the same time in the pipeline. So we simply put in 2 caches in our processors. Now how do we calculate the average memory access time with separate caches? Well, we calculate an average memory access time for the instruction cache and one for the data cache, and then we weight them by how often we access the 2 of them. So if we have an example here, we have 1 cycle cache access time, 100 cycle memory access time. We miss 1% of the time in the instruction cache and 5% in the data cache, and 33% of our instructions are loads or stores. That means that 25% of our data accesses are going to be for data, and 75% of our memory accesses are going to be for instructions. That's because for every 4 instructions, we're going to have for every 3 instructions, we're going to have 3 instruction loads and 1 data load, so 1/4. From this, we can go calculate out what the average memory access time is, and you can see how it works out to 3 in this case. So that is, on average, we're going to spend 3 cycles for every memory access. So let's take a look at some caches in real processors. There's an AMD Bulldozer and an Intel Sandy Bridge. Both of these have large shared caches. The Intel processor has some additional shared caching, and then they have separate caches for instructions and for data. So here you can see the instructions and data caches on the Intel processor. Here's some heterogeneous processors. These are processors that have both CPUs and GPUs on them. And you can see the same thing, large shared caches for instruction and data, and then separate caches for instruction and data so that they can be accessed at the same time. So to review why we have this memory hierarchy, we want to have memory that's both big and fast. To do this, we're going to build a hierarchy where we keep the most important data in the fast memory. That is, we try to move the data we're accessing right now into the cache so we can access it fast. The other data we're going to move into the slow memory. And if we do this correctly, we provide the illusion of a big memory that's also fast. So we saw what we have to work with. We have small SRAM registers, caches, DRAM, flash and hard disk, and these things have very different access speeds. So the very fastest, we have registers and caches, which we can access very quickly, but they're very small. The other end, we have flash and hard disk, which are very slow, but are very large. And the memory hierarchy is about putting these together to get the best average performance. So, how do we make the memory hierarchy work? We talked about 3 different types of caches: fully associative, which are very flexible, but you have to search all the blocks; direct mapped, which have no flexibility, but are easy to search because every block can only go in one place; and set associative. So in set associative, we only have to search a set for each block, so they have a good trade-off in flexibility and complexity. We talked about how we can adjust the block or line size to reduce the overhead of tags. We figure out where data goes in the cache by looking at the address bits. Remember, the last 2 bits determine the byte in the word, and then we have n bits, which determine which word in the cache block or which set, and the remaining bits are for the tag. We have different write policies. We talked about write through, where we write directly to DRAM, which is slow but simple, and write back, which is fast because we keep the data in the cache, but it's more complicated. And we talked about the performance effects of this on the average memory access time.